Okay, thanks for the introduction, and also I want to thank the organizers for the invitation. All right, so this is what I'm going to present. I'm going to talk about some properties of something called effect Hamiltonian. I think most of you know what that is. Okay, so this is so my talk is mainly based on joint works, and also some have been done and some are still ongoing, and collaborations with my friends and the collaborators like Tom Chin Chen, Wei Chen, Song Ting Luo, Hilo, Jian Yan Qian, and Hong Chen, and my colleague Jack. Okay, all right. So first of all, let me quickly review the basic setup. Okay. Oops. All right. Okay. So we have a very standard situation. So we have Hamilton-Jacobi equation that is coercive in this p variable, and here we just look at the periodic environment. All right, so that is well known. This is, I think most people know it. So it was proved by Lyons and Papanicolaou and Varadhan as the epsilon, the prime epsilon goes 0. Then the solution locally uniformly converge to a solution to the effective equation. So especially the original Hamiltonian H that has the spatial variable becomes new Hamiltonian, which the spatial variable is averaged out, right? Okay, so this H bar could be viewed as the nonlinear averaging of this H. Now, this averaging process is very complicated. So we know the existence, but we don't really understand how it goes, right? Okay, all right. So this in the original paper by Lyons, Papanicolaou, Varadhan, I think they call this H bar as the effective Hamiltonian, and then this the same function also appears in literatures in dynamic system. I think this is parallel development. But later on, then people identify, okay, so realize there's connection between the two things. Then this is lead to something called Yifeng theory. Okay, but anyway, so originally, like in dynamic system literature, this H bar has a name called alpha function. All right. Okay, so how we go from the original Hamiltonian H to the this effective one? Conceptually, it is determined by the so-called cell problem, right? Right. So here's the statement. So if you're given any direction P, there exists a unique number. That's the effect Hamiltonian, such that this equation has a periodic solution, right? So the number is unique. We know this number is unique, but the solution might not be unique, even up to constant. Okay, so the V is called so-called corrector. And mathematically, it just captures the oscillation of the gradient, because we know the U epsilon convert to U under the maximum norm, but the gradient of U epsilon only weakly convert the gradient of U, right? So you have the oscillation. So that's captured by V. Okay, now the point is, like, if we just consider the standard setting in the periodic situation, the well-postness is well established, right? So that was settled a long time ago. But of course, like if we talk about the stochastic environment, that's a different story. There are many unsolved problems related to like when you can homogenize, when you cannot homogenize, right? Okay, all right. Okay, so the point is like what I want to talk about is the well-postness in the periodic setting is not the issue. So the main issue, which is the question that remains largely open, is can we go beyond the well-postness and understand detailed properties of the H bar, right? So we only know this guy exists, but we don't know what it is. So especially we want to see how this H bar depends on the original H itself. We know it's a nonlinear average, but we just don't know how this average goes, right? Okay, so this is like a black box. Okay, so now there are multiple reasons that we want to do that. So this I will explain that later. But the one thing is we say, okay, just because of curiosity, right? We want to just understand it. And another reason is sometimes there's physical relevance, and then people want to derive more information. Okay, all right. So we'll focus on the mechanical Hamiltonian. So that's which is interesting enough, and also it's challenging enough. All right. Okay. So if I formulate the question, you say I can formulate in this way. So in the which I call the realization problem. So basically it says, okay, so if I give you a convex function, can you determine whether you are able to find a potential function V such that the effect Hamiltonian is the convex function. So this is so-called realization. Now, there's a subtle issue here. The subtle issue is for this potential V, within which class are we talking about? Are we talking about potential functions, smooth potential functions, or continuous potential functions? All right, so for both cases, it's hard, but there's a big difference. If we talk about smooth functions, that means there are more restrictions, and the solution is much harder. All right. Okay, so anyway, so for us, so we'll focus on smooth potentials. Okay, smooth potentials. All right. This kind of question, it's in spirit, it's not new. Like if we know the first passage population, right? So there's something called a central quantity is called the limiting shape, right? So the existence of limiting shape is known a long time ago. And the main thing, one of the main questions in first positive population is to identify the limiting shape, all right? Okay, right, so especially there's also realization, right? So what kind of convex set can be realized as the limiting shape of some distribution, right, along those edges. Okay, all right. Now we have, so this is the goal. So this is, I put this as the ultimate question. Now there's two ways we can study this problem. One is from the, I call it macroscopic perspective. And the other one is the microscopic perspective. All right, so I will elaborate those things, the second one later. But let's look at the first one. So I try to understand this from a more global point of view. So, okay, the point is, as I said, the main thing is we just want to, essentially is want to understand how this effect Hamiltonian, right? So H bar depends on this potential function V, right? So that's the essential goal. Okay, so from the more larger scale point of view, so I formulate into an inverse problem. So that's what I call the microscopic perspective. Okay, all right. So we can state the question as follows. Okay, so we have this. This one I should put W should V. Okay, doesn't matter. All right. So we have capital V. So that's the potential. So given potential, you get an effective Hamiltonian, right? So I say, okay, suppose you have two potential functions, which are given as V1 and V2. So if they give you the same, exactly the same effect Hamiltonian, what can you say about the relation between V1 and V2, right? Okay, so this is like inverse type question. Well, so if the dimension is 1, this is not hard to figure out because in 1D we have an explicit formula of the effect Hamiltonian. It's expressed in terms of integration, right? So you take derivatives and okay. Anyway, you have an explicit formula. So for 1D, the answer is simple. V1 and V2. They give the same effect Hamiltonian if and only if they have the same distribution, integration. Okay. All right. So we'll focus on higher dimensions when the dimension is bigger or equivalent to 2. Right. So first, we see, okay, so first we ask ourselves whether there's some transformation between potentials which will keep the effect Hamiltonian unchanged. And the only one I know is this trivial one, right? So if we do the rescaling and we do the translation, then obviously you're just going to get the same effect Hamiltonian, right? Because homogenization is rescale things, right? Of course, it doesn't matter if you rescale the potential, right? Rescale the potential. Okay, so now the question is, besides, in addition to this, do we have other invariant transformations for those V's which are non-separable? Non-separable means you cannot write V as just the addition of low dimension functions, right? You have 2D functions, I just can write separable. I write as the sum of a 1D function, then just reduce to 1D. So here I'm talking about those essentially non-separable, those are typical potentials. So the question, do we have another transformation which is not going to change the effect Hamiltonian? Okay, so I don't know, and my guess is probably not. But of course, there's a possibility. Maybe one day someone discovers a magic transformation. So that's like what happened to the 1D shooting operator, right? Like somehow people accidentally find if you go to the KdV equation, then the solution is going to keep the spectrum of the 1D shooting operator, right? So effect Hamiltonian is basically like nonlinear eigenvalue. All right. So anyway, so I believe it's probably that's the only universal transformation that's going to keep the effect Hamiltonian. Okay, so then this leads to the question. Okay, so suppose, like we see again, now we focus on those typical V's. So here I say typical just means those V's which are not separable. You are not able to write as a sum of low dimension functions. All right, so for those typical V's, so question, suppose you know like two effect Hamiltonians are exactly the same. Can you conclude that one actually has to be the translation and scaling of the other, right? So that's the rigidity question. All right, so we first look at the homogeneous case. Homogeneous case is if we know like the effect Hamiltonian is just equivalent to this part, or you can say this part plus a constant. Doesn't matter. So if you subtract constant, so you get 0. Right. So this homogeneous case. Now, for the homogeneous case, it's not that hard to solve, and this is one of the results in the paper I wrote with Han and Song-Ting Roy several years ago. All right, so the answer is yes. Like if the H bar is just the original one, right? So this one, then the V it has to be 0. Okay, so the proof is based on the Hoflex formula and plus a nice application of compression principle. Okay, so the point is like in the homogeneous case, I would say in the kind of trivial case, this is true, right? But of course, the much more interesting situation is the non-homogeneous case. All right, so let's see what can we say about the non-homogeneous case. All right, so this is what we have for the non-homogeneous case. Okay, so this is what we proved. So we proved in 2D. We say, okay, suppose in 2D, and in the case, so this is a very special situation. Okay, so this is a paper I wrote with Han 3 years ago, Han Chen 3 years ago. Okay, so it's a very special situation. It's like a tiny progress. Okay, so we proved like in 2D, if the potentials, they only contain 3 mutually non-parallel Fourier modes, which means we only consider trigonometric polynomials. But that's not that too restrictive because we know that it's dense, right? Those kind of functions are dense. And this is a typical example, right? So this example, you only have 3 mutually non-parallel Fourier modes. So that's one example. So our result says like if in this situation, then we can prove, we can get what we want. So if 2 effect Hamiltonian are the same, then one has to be the rescaling and translation of the other. Now, of course, as I said, like this looks like a very special case, and in fact, well, we expect that this one should be true for any number bigger than no less than 3. So which means if they have the number of non-parallel Fourier modes is no less than 3, you should get this rigidity, but so far we cannot prove it. Because the point is like, even for this special case, it took us a long time to settle it. The computation is just enormous. All right, so of course, like if you say, if you have 3, can you go up from 3 to 4? Well, although like you just add 1 mode, but the computation is going to increase exponentially. All right, anyway. Okay, so this is what we have for the case. Now, in terms of how limited the result is, this is not completely surprising, because if some of you know something called "Can you hear the shape of the drum?" right? So that's also this kind of in the similar spirit. You have a convex domain, and you consider the eigenvalues of the Laplacian operator. Then the question is whether those eigenvalues is able to determine the convex domain, right? Of course, up to a translation, right? So it's a similar. So like our problem, those kind of questions are simply the statement is very simple, but to prove it's really hard. And the issue is lack of tools, right? We don't have the tools, the powerful tools to apply here. So all the previous techniques and tricks we have learned about PDE, they just don't work here. Okay. All right. So anyway, so in the paper that I wrote with Han, actually also appears in a previous paper that we wrote with Song-Ting Roy. So we introduced a method it's called asymptotic expansion. So basically, we look at the effect of Hamiltonian for a very large P and we rescale it. and we try to compare the coefficients. But anyway, so I use that. So you are going to see it in the next slide. All right. So the point is, like, after we use that asymptotic expansion, we are able to reduce the problem to things that's related to combinatorial issues. And also you see it involves essentially just going to some analysis, but it's kind of tedious in plane geometry and the linear algebra. And that's the only, so far, that's the only method we have. All right. So let me explain to you what is the asymptotic expansion that was introduced in the paper I wrote with Hom and Song-Ting, okay, it's the previous one. Okay, so the idea is it's very simple. We say, all right, now because we don't have a form, right? So the main thing is we don't have any really manageable formula for the H bar. Although I said we have a cell problem, that kind of existence, but it's that's more like conceptual. It's not really like can tell you much information. Okay, anyway, so we say, all right, so we look at the function and you're very large, far away from the origin. Now, what's the point of that? The point is like you can do the rescale, right? So if I do the rescale and I divide on both sides, then I get a small parameter. Now, the point is like, if you see a small parameter, then you say, okay, so this is kind of like a lot of things we see in perturbation, like also the Km things. So we can do asymptotic expansion, right? We say, all right, great. So if I just focus on those vectors which satisfy the Diophantine condition, then I can do expansion. I say, all right. So this V epsilon, because if this guy is 0, then you just you can just take this guy to be 0, right? All right. So we start. So we do a perturbation. We have each term that is associated with 1 power of epsilon, right? You can expand this to any order you want. Then, of course, we have corresponding expansion of this effect Hamiltonian. Now, these things are not formal. We are able to make it rigorous. Then we say, okay, so you say, if I put all those things back into the equation, I just compare different terms. Given this Diophantine equation, what I'm going to set up is a group of the main terms linear equations, right? And on the right hand side is some inhomogeneous terms, right? So how we solve those linear equations? We basically go to the Fourier expansion and we solve the coefficients, right? So that's how we solve it, and that's why we needed a Diophantine condition to make sure that those equations are solvable. Okay, all right. So then we expect. If I compare, so it's okay, great. Now I have 1 coefficient, I have 2 coefficients, I have a bunch of coefficients. Each coefficient is going to lead an equation that involves Fourier coefficients of the potential. So you might think that this is great, right? So you get a bunch of equations, right? You have got a sequence of equations. Presumably, you say, oh, that's good. It's going to give a lot of information. But the trouble is, if you write out those expressions, you will see the expression for the coefficients, like those A1, A2, AN, they are going to get more and more complicated. Right? So eventually it's going to a level, it's very hard it's just so messy, it's very hard to extract the useful information. Unless maybe someone one day can discover a very clever way to basically it's kind of combinatorial and those kind of things to combine to make use of those coefficients. But so far, based on what we have a series of equations, but it's but we can only use those equations to some limited level. So the first coefficient A1, that's very simple. It's just the average. Okay, so the first one is just the average of the potential, which is clean. And the second one is it's not as simple as the first one, but it's not bad. Right? If you look at the expression of the second one, it's basically like that. So that's the second one. Okay, the second one. And then you have the third one, fourth one, like the fifth one. You will see the form will become more and more ugly. Okay. Now the point is, if you look at the second one, and then you expect, okay, you see, there is the Fourier mode appears in the denominator, right? So here's a good way, just square. But if you go to the 3, the 4, they will appear like in a lot of combinations, like different combinations, and in different ways they combine together. then we know you have to decouple, right? Decode those combinations to extract things that what we want. Okay, all right. So for our result, if we have, because here we assume there are only 3 modes, right? 3 modes. So for our result, we just need to use the first coefficient, the second coefficient, the third coefficient, and the fourth coefficient. Now, the interesting thing is, like after we use A1, A2, A3, A4, and we found that we are almost get there. We almost got what we want, but there's still a missing piece. So at first we thought, okay, maybe we should just go down to the least, right? A4, we still have just a little bit, it's a little bit away from what we want. So it's okay. So maybe we should just go down the list, right? So go A4 to A5 to A6, right? But then we find if we want to fill that small gap, we need to go all the way to A50, A50. That's like a nightmare, right? There's no way you can do that. So we got stuck there like for a little while. But then we realized, oh, wait a second. There's one piece of information we have not used. That one is not included in the asymptotic expansion. That one is this. So this is a well-known property. Right? So the minimum of H bar, if we look at the mechanical Hamiltonian, the minimum of H bar, oh, sorry, he has not R1, so he has R2 or Rn. Okay, all right, so the minimum function is the maximum of the potential, right? So that's something that is known to, it's well known to experts. It's very easy to prove. All right, so what we find that interesting is after we use this information, then we are able to fill the final gap, and this will give what we want. All right, okay. So that's what we can do in the global level. And as I said, so we conjecture the result should be true if the number of non-parallel modes is no less than 3. But so far, 3 is what we can do. And it looks like if we go along this path, unless we find a very clever and magical way to utilize those coefficients, otherwise, if you just follow what we did here, right? We transfer into those coefficients, and you expect to see there's combinations, and you're going to look at 2D, those vectors, they just interact with each other. I mean, if you have more, then it's going to be really, again, have a mess, like on the plane. So it's not practical if we just, unless we find a new way to utilize those things. Okay, so that's something that we are still, so Ham and I and other collaborators who are still working on that. All right. So next, so this is from the global point of view. So now let's look at the previous question. So the realization question. Right? Let's recall that. The thing is, I want to see what kind of convex functions that could be the effective Hamiltonian associated with a certain smooth potential. Right. So that's what we want is a full characterization. Right. Now, let's say if we compromise, we say, okay, that's probably to get the full picture is probably too ambitious. So maybe we should just be okay at this stage. We should be content with move a little bit. So that means, so this is what I call is find the microscopic perspective. So instead of you get a full list of necessary and sufficient condition when a convex function could be the effective Hamiltonian associated with the potential, let's just find some properties of the effect Hamiltonian, right? Some non-trivial properties of the effect Hamiltonian. So that means, so this is like you try to finish a puzzle, right? Probably have a lot of pieces. So one thing I'm not sure. So at this point is I'm not sure, like whether there's a magic formula or there's like very elegant, clever statement say, if and only if, like when a convex function could be the effect Hamiltonian, or in fact, this statement does not even exist. You have a long list of properties. Okay, you have to satisfy that all the way things to say, oh, in order this one to be a effect Hamiltonian. So that I don't know. Probably it's the second case. Okay, anyway. So then let's say we say why not? We just go ahead to get some properties, right? To just get some partial information, like what kind of special properties that an effective Hamiltonian has to satisfy, right? All right. So then, like for this one, so this one I call the microscopic perspective, because you basically you move, it's like incremental, right? You move a little bit up. Probably you never still like after a lot of efforts, you're still far away from the full picture, but still you make some progress. Okay, so for this one, there are also so like in the project, there are also two directions. So the first direction is we view this as a purely mathematical question, right? So we say, okay, so from the mathematical perspective, we just derive analytic and interesting properties of the effect Hamiltonian and try to get a clearer picture how it looks like. Now this one is related. The property of effect Hamiltonian. So on the other aspect, is closely related to the optimal convergence rate of, this is homogenization, right? So you absolute converge to use, and the fundamental question, how fast you absolute converge to use. So in a very recent paper I wrote with Hilo and Hom, all right, so we will look at several cases, different cases, and especially when the dimension is bigger than 2, and when the dimension is bigger than 2. So we basically find, like, if you want to derive the optimal convergence rate, let's say capital epsilon, then we have to impose some assumptions on the property of H bar. Okay, all right. So that's what we need to derive the convergence rate, the optimal convergence rate. But this is mainly from the mathematical point of view. Now another direction is from the physical point of view. Well, because in some scenarios, the effect Hamiltonian has a clear physical meaning. So that is a project that I have been working with my colleague Jack Xin for over 10 years. So we are looking at something called a G equation. So this is a basic example of a G equation. There are many different forms of G equations, depending on what you want to study, like what kind of physical phenomenon you want to understand. But this is the most basic one. It's a Hamilton-Jacobi equation. All right. So then in this situation, the effect Hamiltonian is a model for something called turbulent flame speed. So what is turbulent flame speed? Well, a simple answer is this. You can interpret this. You think of the spread of wildfire, right? If there's strong wind, the strong wind is going to speed up the spread of fire. So we say, okay, so the propagation speed of the flame on the influence of the ambient fluid, that's what we call the turbulent flame speed, right? So there are many ways to model that, but one way is use the popular G equation in the turbulent combustion community. And then here the A, so there's a parameter. So this one has clear physical meaning. And there's parameter A. So parameter A represents the strength of the flow. For example, the speed of the wind, right? So you want to understand what's the relation of the flame propagation speed and the speed of the wind that is pushing it, right? Okay, so that's one of the main things about the project that I'll be working with Jack. Okay. All right. So for the next part of the talk, I'll just focus on one. So from the mathematical point of view, and we are looking again, as I said before, we just look at the smooth potential, and we try to understand from just mathematically what are the properties that the effect Hamiltonian satisfies. Right? Okay. All right. So first of all, let's look at those rough properties which are well known to experts. Okay. So let's look at those properties. Okay. So these are the properties that has been discovered a long time ago. Okay, so the first one, so the first one is the H bar, right? So the H bar is a convex function. It's a convex function, and it's even, and it glows quadratically. So these properties were proved in the original paper by Lyons, Papanicolaou, and Varadhan, and they are kind of expected, right? Because the original function is 1/2 p squared plus bx. So after averaging, it's not surprising the function is convex, and it's even. It glows quadratically. So those properties, as you probably have seen, like in other homogenization problems, those are called rough properties. It means they more or less inherit those I would say larger scale properties of the original Hamiltonian. The proofs are usually not hard. You can just the proofs are usually based on like comparison principle. and uniqueness of solutions, right? So those were posing this issue. Okay, so for the convex case, the most, on this larger scale, and for any dimension, a very interesting thing, which is different, which means something which is different, which is kind of surprising, right? Which is different from the original Hamiltonian, is the appearance of the flat part. Okay, so but the basic, the original Hamiltonian is H1/2 p square, right? So that's strongly convex. But after you homogenize it, then you find the like for quite general function class of potential functions V, you will find the flat part. The minimum level, it's n dimension. It's a flat piece, right? It's a flat piece. Okay. All right. So but anyway, so the point is like on the larger scale, if you look at a convex. So here, as I said, we only look at a 1/2 p square plus Vx, but this principle applies to all convex Hamiltonians. So basically, the effect Hamiltonian on the larger scale will more or less inherit the properties of the original Hamiltonian. All right. So here I want to mention like if we deal with the non-convex Hamiltonian, then the story is very different. So if you have a non-convex Hamiltonian and you homogenize it, then the resulting effect Hamiltonian on a larger scale is going to be different from the original Hamiltonian. So for example, like in the paper that I wrote with Ham and Jianliang Jin, I think 2 years ago. So we give a kind of systematic discussion about how the effect Hamiltonian of the non-convex cases looks like. So especially you see some dramatic change qualitatively. For example, even the original Hamiltonian is even, the effect Hamiltonian is not going to be even for non-convex. And also like the original Hamiltonian says non-convex, very non-convex, but if you average it, the resulting effect Hamiltonian is going to be like level set convex, which means the nonlinear averaging process is going to crash some non-convexities of the original one. So the point is for the non-convex, it more or less inherits those global properties of the original one. But for the non-convex, it's going to change dramatically to some level. All right. Okay. So, but anyway, so this is the rough property. But now let's look at it more closely, right? So if we try to look at it more closely to see whether you have a change of properties on a small level, right? So detailed changes. Okay, so here's several properties, several detailed properties. So the first one is the first one is okay. So here's the picture, right? If we look at the direction, so it's right here. So if we look at the direction that is not tangent to any level set, so that means, for example, if you just look at the radical direction, and then by using the WKM approach, Craig Evans and Gomez, they proved in a paper that the H bar is strictly convex along the non-tangent direction, which means like for this one, you don't see much difference from the original Hamiltonian. It's strictly convex, but nevertheless, as a more subtle and sophisticated issue is if you look at the level sets. Okay, so if you look at the level sets, then what's going to happen is, so first of all, the level set is still C1, all right, which is okay, which is interesting, but not very surprising. But the more interesting thing is, so that was proved by Bangor, by the C1 is by Kammerer. Okay, so then Bangor in 1994, it's in, Bangor stated the problem in a different situation, but it's essentially equivalent. All right, so basically he showed, like if you look at the level set, for each level set, the level set is not strictly convex. Although the original one, of course, is perfectly circle, right? So it's a 1/2 p squared, so it's a circle. But if you average it, each level set is not strictly convex. Not strictly convex in the sense you always have line segments on the level set, unless your potential V is constant. Okay? So you always, by this averaging process, as long as the V is not constant, you always have a line segment appears on the level set. Okay, all right. So let me quickly tell you that what is the key point in Bangor's proof. Okay, so what is the key point in Bangor's proof? Okay. All right. So the point is this: like I use the Aubry-Mather theory. So he proved in 2D, like if the level set is straight convex. So if the level set is straight convex, that means that will imply geodesics associated with the periodic metric. So this is the periodic metric. It's the minimizing geodesics. We know in general a geodesics might not be a minimizing geodesics, right? Geodesics is just critical point of the function of distance. So if you think of the sphere, right? So each greater circle is a geodesics, but only the minor arc is the minimizing geodesics. But here the point is, so by using the Aubry-Mather theory, I'm going to prove like if this level set is straight convex, then it implies this for this periodic metric, each geodesics is a minimizing geodesics. There's no conjugate point. And then there's a classical result by Hoff in 1947, and he proved like if for every periodic metric, if every geodesics is a minimizing geodesics, then the metric has to be flat. And this is so-called Hoff's conjecture, longer conjecture. So okay, so the equivalent means that V is constant. So here, let me say a little bit. It's not so possible. Okay, so the proof is very involved, it's very sophisticated, but it's not so surprising that you can somehow. It's not completely surprising that you can somehow connect this the level set of the metric. Well, that's because if you look at, so this is a cell problem, right? So if you look at the cell problem, and we know if the Hamilton-Jacobi equation, it has the characteristics. Now, if you look at its global characteristics, it's a minimizing geodesics. Right? Every global characteristics, it's minimizing geodesics. So this basically builds the connection between the cell problem and the dynamic system and the geometry. And this is one of the essential reasons why we have the WKM theory, right? Where we are able to connect the cell problem with the dynamic system. Now, Aubry-Mather theory is basically provides it's a theory that in dynamic system that tells you how those minimizing geodesics are distributed. Right? Okay. All right, so in here, it provides a link between analytical properties of effect Hamiltonian and the geometric things, right? So that's the link is the Aubry-Mather theory. All right, okay, so now, Banger's theory, okay, so let's back to Banger's result. All right, so Banger's result only tells you what happens on each individual level set. It does not really say, because here what we want is the whole function, right? It's not like each individual level set. So there are questions, if you combine all those things together, right, as a whole, like what do you have? Okay, so by combining by refining Banger's arguments and plus some compactness arguments. So I think we can prove the following. So this is something in preparation. So basically, this provides a description of how the 2D effective Hamiltonian looks like. So basically, we can say, typically, it's just a puzzle that is made up of 1D functions. So this is a precise statement. For generic V, you are able to find a dense open set on the plane, such that this dense open set is the union of disjoint open subsets, such that within each small open set, this H bar is a 1D function. So this means it's a 1D function. It only depends on the data product. So here's the picture. It's not complete. This picture is not very accurate, because here we didn't say the whole space can be cut into those disjoint open set. We just said there's a dense open set that are able to cut into piecewise, such that within each piece, it's a 1D function, okay? So here, I didn't say it's a linear function. I didn't say it's piecewise linear. I just say it's piecewise 1D, all right? So that's the picture, typical potential. That's how you get the effective Hamiltonian, right? It's very hard to draw this kind of picture because it's a dense set, right? All right. Okay, so here I use the word generic. So generic is a term that usually does not appear in PD literature, but it appears frequently in dynamic system literature. The point is that, like people in dynamic system, because they are look at very detailed information, they look at very detailed information. Now, it's quite common. Like they want to derive some nice property, but they find there are some bad situations. They have to exclude those bad situations in order to get a nice property. But technically, it's very hard to get rid of those, exclude those bad scenarios. Well, sometimes it's probably even impossible because you can find some counterexamples. So typically what they do is they just do a perturbation. They say, okay, if you're a bad situation, I suppose you're a bad situation, then you just do a perturbation to get it away, so to remove those bad situations, right? So that's what they call generic, right? Essentially just means those bad situations are unstable. Then you can perturb them away, and you'll get so-called typical situations, right? But of course, the good thing is this will allow people to derive nice properties, right? By just technically ignoring those bad situations. But of course, there's a disadvantage. It's although this is kind of say typical generic, but if you face a concrete example, usually no matter how simple the example is, now how explicit this example is, you cannot tell like whether this example is generic or not. So that's the disadvantage. Okay, all right. So that's the 2D, right? So that's the what you say about 2D. Okay, all right. So now let's look at. So the last part, I'll just look at the flat part. So as I said it before, if you look at the larger picture of the effect Hamiltonian, one interesting thing is it has a flat part, right? So the flat part is the minimum level. Right, so the existence of flat part can be easily, people have different ways to derive it. Like if you look at dynamic system literature, they from the dynamic system point of view. But to derive that, it seems to me the quickest way, the easiest way is we use the Infomax formula. I think that this was first proved, by Gomez. I think that's my impression. Okay, okay. So anyway, so this is Infomax formula. It provides one description of the effect Hamiltonian. Now, if you look at this Infomax formula, oh, by the way, it's you can just use maximum principle to prove the. You can look at a cell problem and you just apply the kind of maximum principle to get the Infomax formula. Okay, it's quite nice. All right, so then the point is, if you use the Infomax formula, it's very easy to derive there's a flat part. The reason is, let me just quickly say several sentences. Now, let's see why. So first of all, you see this H bar, because this guy is always positive, right? It's always positive. So that means this guy is going to be always no less than the maximum of V. Okay, so we know the minimum has to be no less than the maximum V. The question is whether this is achievable, right? So what you do is, okay, so let's look at the situation, say V has only finitely many maximum points. So here I put a non-degenerate. So this one is not needed if you just want to get the flat part. So I needed this is for something which is more sophisticated. All right, but anyway, so let's say you have only finite, let's say just 1 point, okay? Because there's not much difference between 1 point and several points. Let's say you have a 1 point, you get the maximum. So what you can do is, okay, so I can just choose the function phi such that the phi equals to negative px, p dot x, right? So that this guy will cancel with each other. Then away from the maximum point, you just glue those pieces together. By keeping this p as small as possible, you will not exceed the maximum v. So the point is, the proof is not hard. If you this just construct the function, a suitable function phi, to get for when the magnitude p is small, then it's always going to the mean. All right. So by now, the point is, what I want to show you is we are going to derive a more detailed property of this minimum level. So first we know that this is convex, right? But then we can ask, but convex, you see, it's just too rough, right? So but we can ask, is it straight convex or not? What can you describe about the boundary of the convex set, right? Okay, now to derive that kind of things, the Infomax formula is nice, but it's too rough. It's too rough to derive if you look at more details, right? Okay, all right. So, but anyway, let me show you. Here's the result, which is again it's in preparation. So this is what we proved. So we proved this not only the level set. The boundary is not only non-convex. No, sorry. So it's not just not straight convex. Actually, the flat line segments. Yeah, flat line segments. They are dense. So the line segments along the boundary is dense. So my picture, of course, is not accurate. If there's no way I can draw like dense line segments. So there's one extreme case is this guy is just rectangular. Right? So that's an extreme case. But the more typical case, what you have is you have a devil's stair, right? So you have a lot of flat piece along you have dense distribution of flat piece along the boundary, and there's no way you can draw it. Okay, so more precisely, what we showed is basically for every rational normal vector along the boundary, except at the most two, for all the other rational normal vectors along the boundary, it's always associated with a line segment. So that's dense, right? So it's okay. All right. So that's what you have. That's the picture. Okay. Of course, like if you just look at the Infomax formula or you just look at the cell property, there's no way you can guess the boundary will look like that. Right? You have such a crazy boundary. Okay, but okay. So now let me. So I have 3 or 4 minutes left. Okay, so now let me quickly show you like why there are these two exceptional rational normal vectors which are not associated with line segments. Okay. So by the way, so this result is optimal, which means indeed we are able to construct one example such that it has exact two. They're opposite to each other because of symmetry. Exactly two exceptional rational vectors, rational normal vectors. All right. As I discussed before, like if you look at the Banker's proof, so basically it's related to the foliation, right? So you're able to use the minimizing geodesics to cover the whole space, right? So it says something related to that. Okay. So anyway. So by those things, there's one key point is that now we can just go to PDE, right? So so one key part in the existence of those exceptional rational normal vectors is this one, right? So this, if you look at this problem, is like kind of pure PDE question. Let's just consider this special potential, right? So it's negative this and this. Now you may ask, oh, this guy is not periodic. But the point is, if you look at those analyses, the only thing that matters is what happens near the critical point. So if you do blow up, so only matters is what is exactly the behavior of V near the origin. So I just blow up. I say I have this kind of things. Okay. Then the question is basically reduced to the following, right? So at some part, okay, it's key part. Now, are you able to find the C1 solution to this equation in the whole space? Well, or you just say near the origin, but doesn't matter. You just do blow up. All right. So such that if you look at its characteristics, right? So are you able to find a C1 solution to this one, such that its characteristics will foliate this guy either this is horizontally or no, this is vertically or horizontally. Right. So the question is, which picture is possible? Either both of them are possible or none of them is possible. Okay. So that's the question. Now, well, it turns out. Okay. So I have 2 more minutes. Okay. So now so let me show you. Let me tell you. So what happens is this picture is possible. This guy is possible, but this one is not possible. All right. So let me tell you why this one is possible. Because I can explicitly construct the function. I can construct this function. This function is a solution to this equation, and if you look at its characteristics, they foliate the R2. Now, I didn't find the function just by guessing the form, use symmetry, and try to match this equation. what I did is, at first I say, what I did is just use the characteristic method, right? You place quite nice boundary condition on the x1, and you look at those characteristics and try to solve it. Now, by a tedious calculation, I find, wait a second, eventually it turns out what you get is a very simple function like that, right? So if you just look at this function, it's not so clear why it satisfies this equation, because you have those things they combine, but it does satisfy the equation, and it gives you this picture. All right, so it's okay. So vertical foliation is okay, but the horizontal foliation is not okay. It's impossible, right? So you are not able to find a smooth function, C1 function to the solution such that its characteristics foliate the horizontally, yes. Now, why this impossible? That's because if you pick 2 points, let's say this point P, this point Q. So if they are very close to the origin, and you say, suppose I say, okay, now because of foliation, right? So you say, okay, I can find the orbit characteristics past P and Q. But the point is, like, if you have the solution to the Hamilton-Jacobi equation, its characteristics minimizing the action. It's very easy to show that. I think it's a well-known fact. It's minimize the action. It has to minimize the action. Nevertheless, if P and Q are very close to the x-axis, by delicate calculation, you will show if I first from P to the origin, so that trajectory, then go from the origin to the Q, another trajectory. If you combine the two trajectories together, the action along this green one, so this is the green one, the action along green one is going to less than the action from the orbit, the red one. So that means this is not going to be the characteristic. All right, so this shows that the horizontal thing is not going to happen. Right. So it's okay. So combine those things and apply some lot of adjustments of Aubry-Mather things, we get what we want. All right. Okay. So that's all I want to talk about today.